Let's see this. I have taken the same problem, but I have changed the number of levels of paging, right? Previously, I had only 2 levels of paging. Now I have changed this to 9 levels of paging, right? See, the intention behind taking this big number is you need to understand one point. In case if I have n levels of paging, then the total number of memory accesses, RAM accesses I need in order to access a byte is nothing but n plus 1, right? Because for n levels of paging we need n memory accesses, because I will refer every level of page table exactly once, and after getting the frame number in which my process is present, which means my byte of process is present, I will go to the process and then I will get the byte, right? So n memory accesses for our page table and 1 memory access for our process. So totally we need n plus 1 memory accesses in order to access a byte in case if I have n levels of paging, right? N levels of paging. So let's see this. They have given the RAM access time, they have given hard disk access time, and they have told that 9 levels of paging is what we have, and they told that page hit percentage equal to 90% or page hit rate equal to 0.9. What does it mean? 90% of the times, what will I do? I will go to 9 levels of paging and then I will go to RAM and then I will get the byte, right? So totally it needs 10 memory accesses. So it will take 10 into RAM access is 10 nanoseconds, right? So 10 into 10 nanoseconds. And 10% of the times, which means in case if the byte is not present inside the RAM, in that case what will happen? We need this 10 into 10, which is 10 into 10 nanoseconds, fine, which means we will access all the 10 levels of RAM, all the 9 levels of RAM along with the process, fine. Also, we will have one hard disk access, right? Because we need to move the data from hard disk to RAM, fine. So for that it will take 1000 nanoseconds, right? It will take 1000 nanoseconds. So what will happen here? These two zeros will get cancelled, fine. It is 90 nanoseconds plus, see, 10 into 10 is 100, fine. 1000 plus 100 is 1100, right? 1000 plus 100 is 1100. So 1100 divided by 100 is 11, right? 1100 divided by 100 is 11, fine. So 11 into 10 is 110. So it is 110 nanoseconds. So 110 plus 90 is nothing but 200 nanoseconds. This is the answer. So in case if I wanted to get a single byte from our computer, it on average it will take 200 nanoseconds. Now let's see, solve using the second method. Coming to second method, definitely I need to access the 9 levels of page tables, right? And also I need to read the data from our RAM, right? Which means I need to read the byte of process from the RAM. So totally it will take 10 memory accesses always, 100% of the times, right? So 100% of the times it will take 10 memory accesses. So 10 into 10 nanoseconds. See, in case if you want, you can also write 100 by 100, right? I'm not writing it. Fine. Now, in case of page fault, which means 10% of the times, I need an additional 1000 nanoseconds, right? I need an additional 1000 nanoseconds. Fine. Now let's simplify this. 10 into 10 is 100 nanoseconds, and both these zeros are getting cancelled. So 10 into 10 is another 100 nanoseconds. So 100 plus 100 is nothing but 200 nanoseconds, right? So we got both as the same answer because both these formulas are exactly same. Fine. The most important point to notice here is this point. In case if we have n levels of paging, then the number of memory accesses or RAM accesses we need in order to get a byte is nothing but n plus 1, where out of this n plus 1, n accesses are needed in order to access the page table and one access for accessing our actual process. Fine.